Well, good morning, everybody. I hope everybody's doing well and you're looking forward to spring break that's coming up here shortly. A couple things I wanted to mention here. And let me see if it applies to you guys because I remember the email just came in last night. So let me just take a look very briefly. So, for those of you who are interested, next semester there'll be one section. When I say next semester, I mean the fall. There'll be one section of 402 taught on ground. I think that will be the 7:30 p.m. section, to be honest with you. And there'll be one section of 410 taught on ground. I think that's going to be the 5:30 p.m. section, and there'll be one section of 420 taught on ground. Again, I think that it's going to be an evening section as well, probably at 5:30. So that's just a heads up. There not a much in the way. There's not much in the way of options as far as on ground offerings, but there you go. We have at least some coming up next semester. And if you're looking at science courses, I have a list of a few. As far as bios, there'll be one bio 400, two bio 430s, 2 to 3 bio 431s, one bio 440, one chem 400, one physics 350, which doesn't apply to you guys. And then 2 physics 411 labs that'll be on ground. So we were in science and mathematics and engineering were given the go ahead to offer some, but not very many classes on ground. So just letting you know, in the fall, you do have some options as far as going to campus if that's what you prefer. I think that most of us would love to be back on ground, but we're kind of taking our time with hopping back on ground, honestly. So, all right. So today, where were we last time? Just rewinding the tape a little bit. Oh yeah, we had just stepped into the divergence test, one of the coolest tests that we have, and at least to test for the divergence of a series. And so I mentioned the fact that every theorem that we're given, you have a contrapositive, and the contrapositive for the well, the contrapositive in general is that if you have a statement if P then Q, the contrapositive is if not Q then not P. That's what a contrapositive means. And so we had a theorem: if our series converges, then the related sequence will converge to 0. And the contrapositive is, and this is the most important, if the related sequence does not converge to 0, then you know your series must diverge, because as time goes on, honestly, you're just adding numbers that are not tending to 0. So you're adding more and more and more and more to your series. So it will diverge. And that is called the divergence test. And that's, I think, basically where we ended the last class. And then I gave an example here where I just said, okay, well, let's prove that this series that we originally started our sequences and series discussions with, let's prove that that series actually does diverge. And the way we did it is we looked at the convergence, not the convergence, but well, actually, yes, we looked at the sequence itself, this piece that I'm highlighting right there. We looked at that sequence and said, well, if n were to go to infinity, does that tend to 0 or does it not? Because if it doesn't, then I know I'm adding numbers that aren't tending to 0 in the long run. And so I'm adding, my sums get larger and larger and larger because I'm adding something non-zero all the time. I can see something here. Hold on a second. I totally forgot. I was in a Zoom meeting yesterday and one of my friends uh, stepped away, and I took a snapshot of his background, and then when he came back, I was in his room. So let me just turn off my background here. I looked up and I was like, that's not where I'm sitting. All right. Okay. So anyhow, so in this case, we found that our sequence did not converge to 0. Instead, it converged to 1, which is not 0. So therefore, the entire series diverges by the divergence test, which I said it's okay to just write by the DT, which is divergence test. All right, so that's where we ended last class. Now we're going to pick back up. Let's go ahead and focus on a given, not series, but a given sequence. Again, I don't see a summation sign here, so I know it's a sequence. And we're asked a few things about this sequence and then its related series. So the first question is the sequence convergent? And it's so important that we have a good idea. This is, so I'm just going to say, is the sequence. I seem to not be able to get my pen size right here. Convergent. I thought I did this morning. I thought I got that all my pen sizes corrected, but apparently not. Okay, so is the sequence convergent? And so what we're going to do is go ahead and take the limit of the sequence. You can actually see that here with the given sequence that it is going to be convergent, but let's just go ahead and use limit notation. So part A, the limit as n tends to infinity of 2n over 3n plus 1. This is one of those cases where I don't require you to use to exchange for x. I really only ask you that you exchange your values of n for x if you're going to use L'Hopital's rule, because L'Hopital's rule requires a continuous set of variables. So not discrete variables to use because you're taking derivatives. But in this case, you're not using L'Hopital's rule, so you can just treat it like a normal limit. We know that this is going to limit to 2/3 very quick, actually. So there we go. We know that it does converge. So yes, it converges to 2/3. Then the question is, well, what if we were to add up all the terms of the sequence forever and ever and ever? Would that converge? And the answer to that is definitely no. So part B, I'll just put no here, and by the divergence test. And that is because since the limit, excuse me, as n tends to infinity of a sub n, the sequence, is equal to 2/3, which is non-zero, then we're constantly adding something like 2/3 as n goes to infinity. Every step of the way, we're continually adding something near to 2/3 to our summation. So therefore, the summation is going to grow without bound. It's going to go off to infinity. So by the divergence test, our summation will be divergent. All right. So that's the divergence test is actually one of the easiest tests to use for convergence. Well, not for convergence, but for divergence in series. And as I've mentioned, divergence and convergence of series is actually the focus of the remainder of this chapter. We're only in section 11.2. So we have, there's 11 sections in this chapter. So we have 10 full sections of does this converge or does it not converge? That's how important that question is. It's very important to know whether a series converges or diverges. If you're wondering why series are so important, it's because, and I wonder if I can adjust my pen size while I'm talking to, it is because the it turns out that every function that we have been introduced to can be rewritten as a series. And often it is much easier to work with a series than it is to work with a function. So you'd like to be able to trade out some nasty old function that you have to integrate or differentiate for a series that you can integrate or differentiate. It's much easier. But to do that, you have to know your series is convergent. That's why we deal with this. That's why there's so many questions surrounding this. It becomes important in engineering, in physics, in signal analysis, all that stuff. So, all right, let's hop forward. Each step of the way, just kind of building up our skills a little bit further. So I'm just opening something in the background because I forgot to open something before we started today. I don't think I actually need to have this open, but just gonna move it off to the side. Give me a moment here. Oh, come on. Now, I can at least start this. Determine whether the following series is convergent or divergent. Very common question for the rest, again, of this chapter. So, is this going to converge or diverge? And if it converges, find its value. So, again, all I'm really going to ask here is one, if I can, I'm going to use a divergence test whenever possible. So I'm going to take a look at this series and quickly just ask, well, if I look at the sequence that it's based upon first, and I were let n to go to infinity, would this become 0? Again, the limit, let's zoom out here. The limit as n tends to infinity of our base sequence, well, because we know that e to the negative nth as n goes to infinity will tend to 0, then we know this is going to be 1/4, and therefore that's not 0. So this diverges immediately. The summation does by the divergence test. You can see how quick these are if they diverge, how quick it is to see that they diverge. I'm not going to say that they're always this easy, but at least in the initial sets of examples, they are kind of this easy. They're pretty fast to go through. So let's try another one here. See if we can ramp up the levels. And let's see, I'm looking at some of my background notes to maybe see if I can find a better. Nope, can't find anything better. All right, so some important recollections from pre-cal. In general, it's incredibly difficult to find a formula for the nth partial sum. In other words, if you added up 10 terms of a series or 1,000 terms of a series, is there a pattern to the summation? But there are some partial sums, it's hard to say, but there are some partial sums that do converge to a certain value or that do have a certain pattern. And these three are the tops. These are the three that you have to have in memory because they do creep up. So the summation of, I think actually all of these you prove in pre-cal, but probably the most interesting one of these is the third one, but I'll just write out this first one. This first one is saying if I added 1 plus 2 plus 3 and added that all the way up to the nth natural number, that is the same as taking the nth natural number, multiplying it by the next number in line, and dividing by 2. And you try that out. You add up 1 through 10, that's going to be 10 times 11 divided by 2. And in fact, this was attributed to Gauss when he was a child, maybe about 10 to 12 years old. He proved this. And so it makes me feel lazy, actually, that he was 10 or 12 years old and he proved something like this. Free time. What are you going to do when you're a kid? You have a lot of free time. All right. So very interesting theorem. Again, this should have been proved by mathematical induction in pre-calculus. And I think of these, the most interesting is this bottom one, which again, you prove in pre-calculus, is saying that if you add up the cubes of the natural numbers all the way up to n cubed, that's the same as n squared times n plus 1 squared over 4. But something you should note about that is that that is actually the square of this. That is, it's going to be, well, if I squared 1 plus n plus 1 plus 2 plus 3 plus so on and so forth all the way up to n, if I took that summation and squared it, that would be the same as the sum of their cubes. So it's a very interesting theorem, incredibly interesting, in fact. So you should have proven these, like I said, in pre-calculus. All three of them can come into play at certain points. So just remember to have those written down so they're at hand. The one that you definitely should memorize is the very first one. Incredibly important. And if you have that in your brain, the third one's pretty easy to remember as well because you're just squaring it. So you're summing the cubes, but you're squaring the result. Anyhow, all of those are going to creep in at some certain point. And then again, reminding you from your pre-calculus course, if anything, this is uh, so much more important than what we just saw, which was a sum of the natural numbers and their squares and their cubes. This one right here is going to dominate some big theory in this course. So the geometric series, the summation n equals 1 to infinity of a times r to the n minus 1, which is equal to a plus ar squared, and so on and so forth, where a is non-zero. That'd be silly if it was zero, is called a geometric series with common ratio r. Now, something I need to mention about this series, the author doesn't make a big stink about it, but I do because I think it's very important to note. Please note that this series starts, let me use green, with a power of 0. So when n equals 1, the power on that common ratio r, that common ratio, oops, it's not, I can't spell common ratio. I'm going to actually shrink down my pen size even further. Anyway, the initial power on that common ratio is going to be 0. So r to the 0th, and then r to the first, and r to the second, and so on and so forth. Very, very important that geometric series start with the 0th power on our common ratio. If it doesn't, we've got some massive issues with computing. So just giving you a heads up. Just adjusting my pen sizes yet again. I get this blue one down here too. Okay. All right. What else do we know about geometric series? Well, if that common ratio is less than 1 in magnitude, that geometric series will actually converge. And that is going to be super important. And that's what this theorem right here says. The sum of a geometric series. The geometric series converges if the common ratio is less than 1 in magnitude. Again, all of this is just a reminder from your pre-calculus course, but it's probably been a while, so that's why I'm talking about it. And its sum will be this summation n equals 1 to infinity of a times r minus 1, and that summation will be a over 1 minus r. I rarely write it as a times or a over 1 minus r. I honestly write this as a times 1 over 1 minus r. There is a strength in doing that. But again, a little bit of a note, the initial power there, initial power must be 0. That's an incredibly important note to be able to use this theorem. Let me zoom out because I think that I might say that. Let's see, for a review of sequences and series without the calculus, including an in-depth review of geometric series, please see our link in the My Open Math course in the, I think it's in the announcements area, because I go through a longer derivation in that area. All right. So let's go ahead and play with these. Determine whether the series converges or diverges, and if convergent, find its value. So this is the non-introductory example. Generally speaking, the introductory example to finding out whether a series converges, or geometric series converges or diverges from pre-calculus looks something like this. Oh, you have some series n equals 1 to infinity of, let's say, 2/3 to the nth power. That's generally example 1, right? And so you start going through this laundry list of questions. Well, that common ratio, which is 2/3, is it less than 1 in magnitude? In other words, if I take its absolute value, is it less than 1? And the answer to that is obviously yes. So the absolute value of r is definitely less than 1, which implies the series will converge. Again, that's from our pre-calculus. So if you're wondering, did you wake up and miss something today? No, you didn't. That's just from your pre-cal prerequisite and So there's a video on that in our announcements area. The second thing I'm going to do is to find out what that, and again, I know I'm not answering the question at hand, but I kind of am in a little way, to figure out what this series, this basic series, converges to. Remember my advice. Actually, it's not even advice. It's what you have to do, is that the initial term has to start with the 0th power. Notice that when n equals 1, I'm not starting with the 0th power. So you have to do something to adjust this slightly. Well, here's the trick, and it's very important that you pay attention here. If I want to reduce this power by 1 so that it starts at the 0th power, then I just factor off 1 power of 2/3 and pull it out of the sequence or the series. That is, I'm just going to write it slowly. Most people wouldn't write it this slowly, but I'm going to write it like this. This is the summation from 1 to infinity of 2/3 times 2/3 to the n minus first. I hope you would agree that when I multiply those two bases together, it basically their powers add, and that's still 2/3 to the nth. So I haven't really done anything other than rewritten it, but I haven't actually changed anything about this series. However, we do have a theorem that says if you have a constant, this in this case just 2/3, times a sequence within a series, which is the sequence within the series is 2/3 to the n minus 1, you can factor that constant out front of the entire series. So basically what I've just said is you can factor constants out. So I factor out a 2/3 to the first power. I'm still summing from 1 to infinity, but now I'm not summing 2/3 to the n, I'm summing 2/3 to the n minus first. And that is the critical step, because now notice this now starts, if I were to plug in n equals 1, it starts at the 0th power. And that's a good thing. So I'm going to say starts now at 0th power. Okay. So because this is starting at the 0th power, okay, hold on a second. It's comical. That is hilarious. Okay. Sorry. If I could speak, I would. So anyway, it starts at the 0th power, and because of that, this can be rewritten as 2/3 times. And now we know from our previous theorem, I'm hopping back just to showcase it. Let's get right here. Something to the a summation to the n minus first power starting at 1 will be written as a times 1 over 1 minus r, where r is a common ratio. So this summation at the top would be written as 2/3, which is the coefficient out front, times 1 over 1 minus the common ratio of 2/3. And then all I do is distribute this 3 into the denominator and the 2 into the numerator. And you see that this series will sum to 2. All right. So what does that have to do with the more complicated version down below? Well, one, I just want to do a basic version first, but this more complex looking version is actually very much like what we just did, because you could use your arithmetic, put a little I'll tell you arithmetic. We're just doing a little bit of arithmetic here and saying that this summation is the same thing as a sum from n equals 1 to infinity of 1 over 3 to the nth plus 2 to the nth over 3 to the nth. So I've just broken up a fraction via my arithmetic. And then we have laws of series. So this series you can split it apart if both splits converge. So I can, if I cross my fingers and hope, I can break this into two series that hopefully converge. If they don't, if one of them diverges, I have to glue this back together. Try something else. Excuse me. So I get down to this part right here, and a lot of people don't, personally, I don't like to work on it like this. So what I'm going to do is I'm going to go ahead and rewrite this through laws of exponents as 1/3 to the nth. And the next one I'm going to write as 2/3 to the nth. And you can see why I did my previous example here, because the summation n equals 1 to infinity of 2/3 to the nth, we actually know is going to converge to 2 from our work up above. So that one's done. I'll just write that off to this. I'll actually write that right now. I'll say that's a summation n equals 1 to infinity of 1/3 to the nth plus 2. And then we still have this summation of 1/3 to the nth. However, remember the common ratio here, which I'll go ahead and point at, that common ratio in absolute value is less than 1, which implies that series will converge. So we continue working on the problem, since we know that series will become something finite. But notice the power doesn't start at 0. It starts at power 1. So I need to factor off 1 power of 1/3. So I'll pull out a 1/3. I'll be left with the summation n equals 1 to infinity of 1/3 to the n minus first. Now notice in this case that the power now starts correctly at a power of 0, so I can use that theorem. Again, you have to start with a power of 0 to use that theorem. And the theorem is going to allow us to rewrite that infinite geometric sum as 1/3 times 1 over 1 minus the common ratio of 3. Distributing in that 3 into that denominator, we'll get 1 over 3 minus 1, which is 1/2, which is 5/2. So this infinite sum from 1 to infinity of 1 plus 2 to the nth over 3 to the nth power, that does actually converge to 2.5. If you add it up forever and ever and ever, it will do that. That's pretty good. I like that a lot. So good example. Nothing that should be terribly mind-blowing, but I hope that's okay. Let me just set something up because, oh, I guess I can't do that. Yeah, I'll just continue forward. All right. So let's see what we have next. And if you do have questions, you can pipe in. It's totally fine. Determine whether the series converges or diverges. Again, if it's convergent, find its value. So this is a really very, very cool looking series. Although to say that you know that this converges or diverges is hard. Remember, the question of convergence is very, very challenging. It's one of the hardest questions in all of mathematics. Does a series converge or does it diverge? Very, very challenging to figure out. But we could still do some arithmetic here and break this into two cases. So I'm going to break this into two possibilities, or not two possibilities, but two fractions. So I'll do a little bit of arithmetic here. Anything else before calculus, basically. Now, I can perform this separation only if each of these sub-series converges. If they do not converge, then I have to glue it back together and figure something out. It is, by the way, very possible that you have a summation like this that when glued together, it converges, but when pulled apart, it diverges. So this is very important that if you pull it apart and you find that a piece diverges, that you know, whoops, I did something wrong. I'll have to glue it back together and see if there's another way that I can showcase whatever I'm trying to showcase. And I'll write that down in a moment because I think that's an important enough statement to write down. Now, whenever I see an n in an exponent, as long as everything else in these series can be written with an n in the exponent, I know that this is geometric. So let me go ahead and rewrite that with n's in the exponents of everything in that series. So to showcase what I mean, I'm going to write this as 1 over e to the nth power. Once I write it like that, I immediately know that this entire series right here is a geometric series. And so now I know what I'm hunting for. I'm hunting for the common ratio for that specific series to be less than 1, which it is, because 1 over e is definitely less than 1 in magnitude. And so I know it will converge, and I can find what that specific piece converges to. But we still have this second piece that seems to be a little disconcerting. Wonder if you could possibly think of a way to do this. And just remember that everything you've learned in this course is fair game. Well, I mean, you're not going to integrate something, but you've learned techniques. Yeah. So Raj just said it. Partial fraction decomposition. Yeah. Partial fraction decomposition. Pull that sucker apart into 2 different fractions, and you might find out something beautiful. So I'm going to teach you a trick now. Normally, I don't like to teach tricks because, generally speaking, tricks don't always work, and so they're great on individual, like, rare cases, but they don't always work. So I don't like to teach tricks. However, once you've learned the stuff that you're already learned and you've worked on it for a while, then I feel like it's okay to say, okay, now there's a faster way to do this. So let me take a drink, and then I will show you a trick. Now, I hope you remember that when we went through by parts, integration by parts, let's start with that conversation. When we went through that, I taught you a trick. Let's say that you had a polynomial x squared plus x plus 1, and as part of your integrand, and maybe let's put a sine of x as part of your integrand as well. I taught you a trick that you could use for integration by parts, because as long as you have a polynomial times either a trig function or an exponential function, you can do this little trick to make by parts a little bit easier. It really doesn't work for a lot of cases, but when it's polynomial times something, it does work out. So the way it worked was like this. You would have u and dv, and you would choose something to differentiate, which would be the polynomial. And you would start taking derivatives, right? So the derivative of x squared plus x plus 1 is 2x plus 1. The derivative of 2x plus 1 is 2, and the derivative of 2 is 0. And then you would look at that integrand and you say, I need to integrate a piece too. Well, we're going to obviously integrate the sine of x, and the integral of sine of x is a negative cosine of x. And the antiderivative of a negative cosine of x is a negative sine of x. And the antiderivative of a negative sine of x is a cosine of x. And then we did this. Get my green pen out. Green means we're going to add. So we'd add the product of those two, and we'd subtract the product of these two, and we'd add the product of those two, and that would actually be the full integral. So that was the trick if you had polynomials times anything else, pretty much. So adding the product of negative cosine in that polynomial, you would get a negative x squared plus x plus 1 times the cosine. And then we would subtract the product of negative sine and 2x plus 1. So unfortunately, subtract a negative, we'd get a positive, and then 2x plus 1 sine of x. And then finally, we would add, add 2 times cosine of x. And then plus c. All right, so that was a trick there. Again, the trick doesn't work in all circumstances, but it works when it's a polynomial times a trig or exponential function. Now there's not a similar, but there's a trick also when you're doing partial fraction decomposition. So let's suppose that you were integrating 1 over, and I'm going to steal the fraction that we're working with up here. 1 over x times x plus 1 is what I'm going to write down. Dx. Now, what you were taught to do was this. Oh, I have this 1 over x times x plus 1, and that's equal to some number over x plus a different number over x plus 1. And you'd multiply both sides by the LCD, so you'd get 1 is equal to a times x plus 1 plus b times x, and then you do strategic substitutions. So for x equals 0, this is actually pretty fast, so there's no real reason to have a trick here, but for x equals 0, you have 1 is equal to a, and for x equals -1, you have 1 is equal to a negative b, or in other words, b is equal to a -1. Great. And then we know that this fraction would be written as 1 over x plus a -1 over x plus 1. And we go through and do all that stuff. But there's an actual faster way of doing that. The faster way works like this. It's really actually somewhat challenging to describe without me being in front of a whiteboard. I did this last semester, in the previous semester for my Calc 2 students. And it's just very challenging without me jumping in front of a whiteboard and doing a bunch of stuff. So here we go. We're going to deal with what's called a residual. The residuals are basically what's left over after you turn off your denominator. So look at this denominator here and think, what would you plug in to turn off the denominator? Well, there are two options, 0 and -1. So if you let x equal 0, what you would get if you covered that up, so let me go ahead and just cover that up. Use a black highlighter for that. Actually, let me make my black highlighter a little bit larger so I can erase it. Okay, so I cover that up, letting x equal 0. And the fraction, if you were to cover that up and allow x to be 0, your fraction would become a 1 over 0 plus 1, which is just 1 over 1. Notice, same thing. Now, if you were to say, okay, well, let me find the other residual is what we'd call that. So you're going to let x equal -1, and you're going to cover up that piece right there. If you let x equal -1, which would turn off this denominator, you would have 1 over a -1. And that goes in the numerator of what it would turn off. So again, I'll go through another example in a moment, but you can see how quickly that does a partial fraction decomposition. Okay, I'll give another example in a moment, but for right now, I'm going to just note that our, let me get my highlighter back. I'm going to note that our partial fraction decomposition is 1 over x plus -1 over x plus 1. Now, you can extend this out to very, very large and terrible partial fraction decompositions. So, for example, this is another one. It's a very powerful technique. So let's say you were integrating 3x minus 2 over x plus 4 times x minus 2 times x plus 1. Okay, dx. And you had to do a partial fraction decomposition. Well, you know how it's going to decompose. It's something over x plus something over x plus 4 plus something over x minus 2 plus something over x plus 1. And officially, by the way, this method is called the Heaviside cover-up method, and not Heaviside like that's an imaginary name. That's somebody's name, actually, Heaviside. And so the way this is done is you cover up the denominator. So the denominator I'm going to focus on right now is the x. I'm going to cover up that x. You go ahead and just cover it up here. Okay. So I've covered up that x. Now, what would have caused that x to become 0? Well, it seems pretty obvious what causes x to become 0 when you're just dealing with x. It's x equals 0. So what we're going to do is allow x to be 0 in this fraction here. If you allow x to be 0, what do you get? Well, you get a -2 in its numerator. In its denominator, you get a 4 times a -2 times a 1. That is actually going to be the decomposition, or the numerator of the decomposition for a over x. And if I go on to the next one, I say, well, I need the numerator for this x plus 4 right there. So I'll let x equal -4. So again, I will cover up the x plus 4 right here. I'm going to let x equal -4 in this integrand, and that will tell me the numerator of x plus 4. So if you let x equal -4, I'll get -12 minus 2, which is a -14. Let me go ahead and write that down. Over -4 times a -6. I'll just write that. -4 times a -6 times -3. Pretty cool method. And it's actually not too bad to see why it works, but let me just go ahead and finish this out in a moment, or really quickly. So to showcase how quickly it would go if you're really barreling through, I would then let x equal 2. So I get 6 minus 2, which is 4, over 6 times 2, which is 12, times 3, which is 36. And now I'm going to move on to x equals -1. Let me cover up this piece right here. So if x were -1, I'd have -3 minus 2, which is a -5, over, let's see, I'm at x equals -1, right? So 3 times a -1, so it's a -3, times a -3, which is a +9. And there's my partial fraction decomposition. No system of equations needed, nothing. It's a really, really cool method. If you're wondering why it works, it actually works because of something super simple. If you had originally written it as ax plus bx over 4 and so on and so forth, when you would multiply both sides by the LCD, you would get the following: 3x minus 2 is equal to a times, it's usually over x, but it would have been, the x's would have canceled, so you would have x plus 4 times x minus 2 times x plus 1, plus, then b would have been written over the x plus 4, and when you multiply both sides by the LCD, the x plus 4s would cancel, and you'd have x times x minus 2 times x plus 1, plus c, but that would have been over x minus 2, multiplying both sides by the LCD, x minus 2s would cancel, and you have x times x plus 4 times x plus 1. And finally, plus d, and d is over x plus 1. So when you multiply both sides by the LCD, x plus 1s will cancel, and you're left with x times x plus 4 times x minus 2. Now, if you take a look at this, to find the value of a here, I need this stuff attached to a to not disappear. I need everything else to disappear. Everything else disappears when I let x equal 0, which happens to be what turns off the denominator for a. And that's why when you find what what a is equal to, you're letting x be the denominator of a. All this other stuff turns off, it disappears, and you end up getting a times 0 plus 4 times 0 minus 2 times 0 plus 1 is equal to 3 times 0 minus 2. Or in other words, -2. A is -2 over 4 times -2 times 1, which is exactly what we got. So that is kind of a not a proof, but a good kind of clean justification as to why the method sort of works. Really neat way of doing it. So Avi's asking, does this work for other types of denominators, like the irreducible quadratics and stuff like that? No, it doesn't. But all is not lost. It still sort of works. So let's suppose that you had an integral instead of 3x minus 2 over that stuff. Let's suppose that it was like this. X times x minus 2 times, let's have an x squared plus 1 dx. Okay. I know that this is going to break into something over x plus something over x minus 2 plus. This method does not work with irreducible quadratics. So I'm going to say plus ax plus b over x squared plus 1, because I will have to actually find out what ax plus b is. I'll still have to do that. So going through this, I will say, all right, great. If x were 0, Heaviside cover-up method, if x were 0, what would I get? Well, I would get negative 2 over negative 2 times 1. Pretty awesome. And then next one in line, if x were 2, what would I get? Well, in the numerator, I'd get 6 minus 2, which is 4, over 2 times x is 2, right? Yeah. So this is going to be 4 plus 1, which is 5, times 2, which is 10. So I've already gotten 2 of my numerators done. So at this point, I can't use Heaviside cover-up method to find ax plus b. However, my amount of work has been reduced. Now I would just say, okay, well, you know what this implies? It implies 3x minus 2 is equal to negative 2 over negative 2 is 1. And that was over x, but I'm going to multiply both sides by the LCD. Plus 4/10, which is 2/5. But that was over x minus 2. When I multiply both sides by the LCD, I get x times x squared plus 1. And then I have this quantity ax plus b. It was over x squared plus 1, but we're multiplying both sides by the LCD, so I'm left with x times x minus 2. And now I just select 2 random values for x to plug in. They cannot be 0 or 2. So I'm going to plug in 1 and negative 1. That will give me A and B. So that's a good tactic. It really reduces the amount of work you have to do. So to answer Avi's question, yeah, you can't use it for everything. That's why it's a trick and not a rule, right? But it really does speed things up. So really cool method. It also doesn't work really well if you have powers on X. So I know I'm making this a huge aside, but we have the time today because we only have 2 more pages beyond this in lecture. So I wanted to give you this trick today. So because it's very useful when dealing with sequences and series. And you've already shown me you know how to do partial fraction decomposition. So now I can allow you a trick. That's my kind of rule of thumb, is if I've seen your skills now I feel okay of saying to you, okay, you're allowed to use this trick. Let me just see something really quickly. All right, perfect. So to describe what you would do, let me actually rope that up. It's a little bit cleaner and easier. To describe what you would do if it's powers in the denominator. So let's say that you had a 3x minus 2 over x squared times x minus 2 dx. So that is slightly different, right? We know that this is going to be something over x plus something over x squared plus something over x minus 2 dx. The problem here is that when you use the Heaviside cover-up method, it will only find the numerators of highest powers. So it's not going to find this numerator right here. A is terrible. It's not going to find this numerator right here. So the Heaviside cover-up method, again, I'll write that in. Heaviside cover-up method only finds the numerator of highest power. on a factor. Okay. So in this case, again, I would still use the heaviside cover-up method. I'd let x equal 0. If you let x equal 0, you get -2 over -2. That's pretty awesome. And then if I do the heaviside cover-up to let x equal 2, I will get 6 minus 2, which is 4, over 2 squared, which is 4. So look, I've already found 2 of my numerators. So now just to find the last numerator, I can plug in any x value I want. Remember, it looks sort of like this. You have 3x minus 2 is equal to a. A was over x. So it's going to be, when you multiply by the LCD, you'll have a single power of x on here times x minus 2. Plus 1, that was over x squared, which will cancel with the x squared. You'll be left with an x minus 2. And then plus 1, and that was over x minus 2. So you have an x squared. And now just let x equal 1, and you'll find out what a is. Really very fast method. I know that you're like, man, why didn't you teach this when we were in, doing the last exam? Well, it's because I want to see your skills before you start using this trick. That's a very cool, very, very cool trick. All right, all that kind of trick work, only to go back to this guy right here and just say, all right, can we taffy pull that apart? Let's see, we have a summation of we have a geometric series here. Notice the power on this does not start at 0, so I'm going to factor out 1 over e. Oops, this one equals 1 over e. So I've reduced the power within this summation by 1. So this is 1 over e to the n minus first power, which means now this is good. It's starting at the 0th power. That's green means good there. And plus the summation n equals 1 to infinity of something over n. I know we've already pulled this apart, but I'm just doing it this one last time just to showcase it. So we are going to pull this apart into 2 separate fractions. If n were 0, we'd have 1 over 1. If n were -1, we'd have 1 over a -1. Let's see. So this becomes 1 over e times, since this is now a geometric series right here that starts at the power 0, I can trade it out for a 1 over 1 minus its common ratio, which is 1 over e. And this power series, or I shouldn't use that phrase power series yet. This series, 1 over n minus 1 over n plus 1, again, very, very, very challenging to find out what this series would sum to, if you could even begin to find out what this series will sum to. However, this if you're looking at a series and it's a sum or a difference of fractions, or a sum or a difference of anything, I would write out a few terms. By the way, this e will distribute in, so I'm going to do 1 over e minus 1 here, plus, watch when I write out a few terms of this series. If I add it up, letting n equal 1, I'd get 1 minus 1/2. Now, letting n equal 2, I get 1/2 plus 1/2 minus 1 over 3. Let n equal 3, I get plus 1/3 minus 1 over 4. Let n equal 4, I get plus 1/4 minus 1/5, ... right? Now remember, you're allowing n to go to infinity. Notice -1/2 cancels with +1/2. -1/3 cancels with +1/3. -1/4 cancels with +1/4. -1/5 will cancel the +1/5, and so on and so forth down the line. So that infinite sum actually is like saying this. I'm taking the limit as n goes to infinity. The first term is always 1, And then we're always going to lose 1 over n plus 1. Everything else between 1 and 1 over n plus 1 is canceling out. In other words, if n is a billion, the 1/2's canceled, the 1/3's canceled, the 1 over 4's canceled, the 1 over 5's canceled, so on and so forth down the line, all the way to 1 over a billion. Those all cancel. The only thing we have at the end is the very last term in that series, which is 1 over n plus n goes to infinity. That will tend to 0. And you get this. Oops, there's a plus there. That is the sum of this series. It converges to 1 over e minus 1 plus 1. Really very cool series. It's got that telescoping piece to it. You know you have, yeah, there's telescoping. Yep, exactly. So, or I shouldn't say but it's a good indication. Sorry, I'm stretching. Hold on. Early morning stretch. That was a good one. You know that you have the possibility for a telescoping series if you have to do a partial fraction decomposition. That is a good hint that you might have stuff that cancels, terms that kind of cancel each other off. You'll see all different versions of telescoping series in this homework. So just letting you know, keep your eye out for telescoping series. I think there are like 4 problems with them. So be highly aware of that. All right. By the way, I hope that trick is cool. I hope that you like that little trick. It's really meant to speed up your computations as you move through. You're going to have to use that trick, by the way, in your differential equations course, because in differential equations you do deal with series, and being able to pull them apart quickly is a skill that you're wanting to embrace. You want to just rip them apart very quickly into their partial fraction decomposition. Practice it. It's super awesome. And it's great because then on the final exam, you're going to be like, man, I'm just going to break that apart using this little trick. That's perfectly fine. I don't mind. That's totally okay. All right. Let's go to the second to last example here in this section. And so it's I don't know if you've ever watched it. There's a great movie. I'm sure you probably have watched it, called The Wizard of Oz. Okay. And there's a little wizard in The Wizard of Oz who kind of controls a lot of stuff in the world. And it's when people say that you're opening the curtain, it's referencing The Wizard of Oz. So we're going to reveal a little bit by kind of peering or opening the curtain a little bit here. This is what we would call a power series. This is actually something from 11.9 and 11.10. This is what we're going to eventually deal with. Notice that this series, which it is a series because it's got this summation symbol on it, this series is a function of x. So it represents a function. Like if I said, what's f of 2, you could plug 2 in, although that would be kind of a pain to kind of deal with, but you could totally do that. Or if I said, what's f of, I can't say 0 because we have division by 0 here, but if I said, what's f of 0.1, you could plug in 0.1 and so on and so forth. These series, these are called power series. These power series are our ultimate goal. We want to arrive here and play with these at the end of this chapter. So let's start with a very simple question. How can we make it converge? I want this to converge. Again, to reiterate something I mentioned earlier, it is incredibly difficult to showcase that a series converges normally. It's kind of easy to showcase it diverges because you could use the divergence test. Not all the time, but some of the times. But to showcase what a series converges and what it converges to is incredibly difficult and rare. You have to have a very special type of series to be able to do that. And that very special type of series is a geometric series. Because we happen to know that the geometric series of the form some number a, which I hate writing in there. I'm going to write it out front. Some number a times r to the n minus 1. We know that converges if the absolute value of r is less than 1, and we know it converges to a times 1 over 1 minus r. That's the only type of series that we can really say, yep, I know exactly what it converges to. All other series, bets are off. We do not know what they converge to. So you want most of your series to be geometric if you can get them. Well, if you take a look at the series I've handed you here, it does have powers of n all over the place. This is likely geometric. What I need to do is recognize a few dangerous pitfalls. One, n starts at 3. Not a big deal, actually. Generally speaking, when you're dealing with a series, I don't care where it starts. I don't care if it starts at 3 or 3 million. I'm not really that concerned about it. But if somebody then says, it's geometric and I need to know its exact value, that's when I get a little concerned, because finding the exact value of a geometric series requires that the first power be 0. I mean, point and arrow must start at 0. I don't care what this number is, as long as when I plug it in, it starts at 0. And since it's 1, when I plug 1 in, that totally starts at 0. So I can apply this theorem there. So let's see. I'm starting at 3. There are 2 issues. The first thing I'm going to do is make sure that both numerator and denominator start with the same style of power. So let me just write that off to the side. First thing I'm going to do is force numerator and denominator to start at same power. That just is, trust me, a lot nicer to start with that simple tactic. Notice x is starting to the power of n minus 1, while 2 is starting to the power of n. I could subtract 1 from that power if I want to, if I pull a power of 2 out front. So that's what I'm going to start with. I'm going to say that this summation, which I'm trying to zoom out, there we go, is equal to 2 times the summation n equals 3 to infinity of 2, not to the n anymore, because I pulled off a power, it's to the n minus 1 over x to the n minus 1. That's what I mean by this first step. Just force that numerator and denominator to start at the same power. It doesn't have to start the 0th power initially, but we're going to manipulate it so it does. But I just want it to start at the same power. In fact, I'm going to go ahead and write this as 2 times the summation n equals 3 to infinity of 2 over x to the n minus 1. Now it's really starting to look geometric. And remember, our goal here is if somebody says, find the sum of the series, which they're really saying here, then I really want to kind of start compressing it down so it looks like this theorem up here. So let's see. The problem I have is that this is not starting at a power of 0. It's starting at a power of 2. When n is equal to 3, I'm starting not at a power of 0, but a power of 2. So I'd like to subtract 2 powers off of that if I could. And the way you do that is to pull 2 powers out. So let me say that. So pull 2 powers. Come on, screen. There we go. Out. So I'm going to take that 2 over x, and I'm going to pull 2 powers of that out front. So 2 times 2 over x to the second power, because I'm pulling out 2 powers. That will reduce the power within the summation by 2 more. And notice, now my series is starting at the 0th power. Perfect. That's what I want. So now I can say this definitely, I can force this to converge. No, Avi's asking a really good question in chat. She's asking, does this, are we assuming that X is a constant? No, we're not assuming anything about X. So we must state something. We know this is going to converge if the common ratio, which is 2 over X, is less than 1 in magnitude. I'm going to write that down. Okay, so, oh, by the way, I forgot to mention my second step here. The first step was to force the numerator and denominator to start at the same power. The second step was to then force the power to start at 0. By factoring out, if necessary or if needed. So that's what we did. We started by getting the numerator and denominator to have the same power, n minus 1. And then we saw that it wasn't starting at the 0th power, starting at the second power. So we pulled out 2 powers of that common ratio so that now it does start at the 0th power. The third thing we need to note here is convergence will happen. Convergence is guaranteed if the common ratio in absolute value is less than R. So our common ratio involves an unknown X. Common ratio here is 2 over X. And we want the absolute value of that 2 over X to be less than 1. Whoops, that's a weird looking 1. In other words, we want, I'll just take the reciprocal of both sides because I want to solve for X eventually. We want X over 2 to be greater than 1 in absolute value, sorry. If you multiply both sides by 2, that means you want the absolute value of X to be greater than 2, which tells us that either X is greater than 2 or X is less than negative 2. Gosh, that negative is not looking good to me. So again, the question is, when will this series converge? Well, it will converge as long as you're dealing with X's that somebody's plugging in that are greater than 2 or less than negative 2. Notice that my algebra came into play. The algebra with absolute value inequalities, that comes into play in calculus a little bit, specifically here. So anyway, we know that this series will converge as long as X is greater than 2 or less than negative 2. And what will it converge to? Well, let's see. We have 2 times 2 over X being squared times. Well, I know that if this converges, this series here converges, it's going to converge to 1 over 1 minus the common ratio. Again, that's if X is greater than 2 or X is less than negative 2. I'm going to go ahead and clean this up. That's a 2 squared times 2 times 1, so an 8 in the numerator. And I have an X squared here, and I'm going to distribute it across in the denominator. So an X squared minus 2X, or in other words, 8 over X times X minus 2. So what I want to drive home is something incredibly fascinating. We have a function somebody handed us, but they didn't hand us this function in a form we've ever seen before. They've handed us a function starting at 3, going to infinity, and it's 2 to the nth over X to the n minus 1. And we have found that this is actually the same thing as 8 over X times X minus 2. It's only that same thing, by the way, if what we're plugging in is greater than 2 or what we're plugging in is less than -2. Now, what does this mean for the future of mathematics for you? It means if you have a terrible function, and this is not so terrible, you could totally, let's say that you were asked to integrate this. You could totally integrate this. It's not that big of a deal to integrate. Okay. And you can differentiate this too. All right. But we have options now. If somebody said, I need you to integrate this, I would say, well, yeah, I suppose I could integrate that. Or since I know that this is the same as, this is not part of this section, so you can kind of stop writing if you handwrite notes. You can just watch this for a moment. Since I know that 8 over x times x minus 2 is equal to summation, starting at 3, I know it's equal to the following: 2 to the third over x to the second plus 2 to the fourth over x to the third plus 2 to the fifth over x to the fourth plus ... That's what this summation expands out to be. And if I wanted to integrate this, let's pretend as though I wanted to integrate that function there. That x is going to bother me, so let me clean that up. Instead, I could integrate the summation. And actually, I'm going to write it this way. And this is actually a lot easier to integrate. Just add 1 to powers, divide by new powers. It's like you're integrating a polynomial in a way. And that's the power of dealing with series in the long run. If imagine somebody hands you a terrible function, I mean, really terrible, like integral of sine inverse of e to the x squared plus x minus natural log of x, or something like that. I have no idea. Okay. If I can find a series representation of this, which is just an infinitely long polynomial, basically, then the integral is actually pretty easy. And that's what we're going to try to do in the long run, is exchange terrible looking functions for polynomials. Or in this case, it's not really a polynomial because it has negative exponents, but close enough. So anyhow, that's just a heads up of where we're heading. It's not in this section, so don't sweat it. What is in this section is a problem like this, where I say, hey, guess what? F of x is equal to the summation. I wonder if it will ever converge. Show me that it can converge and tell me when that happens and what it converges to. Well, to show me that something converges, it's going to have to be geometric. So you're going to have to follow these steps off to the left, force the numerator and denominator to start the same power. And then once you have that done, you force the power to start at 0 by factoring something else. So that's what we did right here. Now that we have that starting at a power of 0, that summation, we know that converges. We know what it converges to, and we know when it converges, when that common ratio is less than 1. Solve that, and you find out when it converges and what it converges to. Really a very, very beautiful process. Okay, I hope that's interesting. I find it to be one of the more interesting parts of this entire course, honestly, and also a very useful part. The very last question is some heavy theory, not theorem, but theory. The Cantor set. So this is kind of a bonus statement here. The Cantor set is constructed by first removing the open interval 1/3 to 2/3 from the closed interval 0 to 1. Let me showcase this using my handy dandy ruler here. So we have a closed interval from 0 to 1. Let me go ahead and just make this my full length interval. The problem with this is that I'm going to be doing a lot of erasing. So let me at least do this. That's from 0 to 1. It's a closed interval. 0 to 1. Okay. And I am going to remove the middle third because that's what the Cantor set is, how it's constructed. You take this closed interval from 0 to 1, and you're going to remove the open interval 1/3 to 2/3. So let's go ahead and erase the open interval from 1/3 to 2/3. So let's mark where 1/3 is. I'm going to probably say it's about here. And here's probably about 2/3. I don't need to be exact here. Actually, that's not good. I didn't want to be this exact, but I'll be somewhat exact here. So something like this. Something like that's still not good. Whatever. Okay, we'll just pretend as though that's good enough. Okay, 1/3 and 2/3. And we're going to erase the open centered interval. Now, when I do that, I'm just going to quickly do something here so that I can just erase. Okay. Oh, all right. Great. Now I know that's not symmetric. I totally get it. Forgive me. Okay. Now, what else do we do with the Cantor set? Seems like a very simple problem if I just said take a length from 0 to 1 and erase the open interval in the center. Well, there's more to it. So now notice that we have an interval from 0 to 1/3, closed interval, and we also have a closed interval from 2/3 to 1. Not bad. Well, let's go ahead and remove the middle third of each of these two intervals. So the middle third, well, what's a third of a third? That'd be a ninth up to 2/9. So we're going to erase this middle third of this length, this full closed interval length here. Let's go ahead and erase that middle third. And we'll do the same thing over here. So I'm going to cut out these right here. This will be 8/9. This will be 7/9. And we're going to go ahead and keep the left and right edges of this, but cut out the middle third. And you can see, there we go, what we have left. Remember, we started with a full length from 0 to 1. And that's the interval we have, 0 to 1/9, union 2/9 to 1/3, union 2/3 is 7/9, and then union 8/9 to 1, and so on and so forth. Well, what happens here if we continue this process? That is, now I'm going to remove the middle third of this one. Well, that would be 1/3 of 1/9, which is 1/27. This would be 2/27. And we're going to remove the middle third there. Next one. Let's see, that's 7/27 and 8/27. We're just going to remove the middle third here. Next one. Let's see, 9, 18, 19/27 and 20/27. Again, removing the middle third. And finally, 3, 24, 25/27 and 26/27. Again, remove the middle third. And we could do this all day long, right? Each of these we can continually remove middle thirds. And that's what we're actually going to do. So let's sum up all of the stuff, the intervals being removed. Okay, well, initially we had a length of 1 and we cut out a third. So we lost a third. That was step 1. We lost a third. Okay. Step 2, so after we lost the third and we had these outer edges here, we lost a third of a third here, this central area right here. We lost a third of a third. So on step 2, that's 1/3 of 1/3. But actually, we did that twice because we lost a third of a third over here. So we lost 2 sets of a third because we had 2 of those. We had a couple splits, and each split we lost a third of. And that was a third of that third. Now notice how many splits we have now. We have 4 splits. So in our third step, we're going to lose remember, this length right here is a third of a third, or in other words, a length of 1/9. And we're going to lose a third of that length. So in this third step, we're losing a third of a third of a third, and we're losing that in 1, 2, 3, 4 intervals. Now you can probably see the pattern now. This is 1/3 to the first times 2 to the 0th plus 2 to the first times 1/3 squared plus 2 to the second times 1/3 cubed. The next step, if we had written it out, we would have lost 2 to the third times 1/3 to the fourth. That's how many little slices we would have cut out and the length of those slices. And we would do that forever. We just continue cutting and slicing like that. Writing this as a summation, this would be the sum. I'm going to actually start it at 1 and go to infinity, although you could technically start it at 0 if you wanted to. It doesn't really matter. And I'm summing up 2 to the n minus 1 because it starts actually when n is equal to 1 as 2 to the 0th. When n is equal to 2, it's 2 to the first. So that does work out. And 1/3 to the nth. Again, because it starts power 1, then power 2, and so on and so forth. That summation represents how much of that interval I've removed if I do this an infinite number of times, if I keep cutting all day long. Well, let's go ahead and get those to have the same power. So to get them to have the same power, well, I have a 2 to the n minus 1. I'll go ahead and factor off a power of 1/3. So I have a 1/3 to the n minus 1 as well. And we could use just laws of exponents here, glue those two things there. So a little bit of algebra. We know this is 1/3 summation, n equals 1 to infinity of 2/3 to the n minus first. Now, before I finish out this problem, which will happen very quickly, I just want to make a very important note here. As we were cutting slices away from these intervals, we kept the edges. Notice every single time that I did this, I kept 0. I'm going to keep 1/27th. I'm going to keep 2/27ths. My interval is going to keep 1/9. My interval is going to keep 2/9 forever and ever, and 7/27ths and 8/27ths and 1/3 and da 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 da. The more slices I have, the more points that I'm going to keep. I'm going to keep everything in blue here forever and ever and ever. No matter how many slices, I still keep, in fact, every time I make a slice, let's see, my initial slice, I had 0 and 1 that I kept, right? And then, or at least my initial interval. And then when I cut, I then got to keep 1/3 and 2/3. So I doubled up the number of points that I'm keeping. And then the next slice, I doubled up the points I was keeping by keeping 1/9 here and 2/9 there, and so on and so forth. So really every step of the way, I'm doubling up the number of points that remain. Okay. The number of edges. Let's go ahead and see what I've removed though. Well, we know because it's a geometric series, this is going to be 1/3 times, since it's starting at power 0, times 1/1 minus 2/3. Again, common ratio is less than 1 in magnitude, so I know it's going to converge. Distribute the 3 in, and I'll get 1/3 minus 2, or 1. Punchline. We have removed, over an infinite amount of time, we have removed 1 full length of the interval 0 to 1. We've removed, as n goes to infinity, we've removed the entire interval. Yet, we will have an infinite number of points remaining that we haven't removed, because of all these edges will always remain. Specifically 0, 1/3, 1/9, 1/27, 27 times 1/81st, 1/243rd, ... and a bunch of others, by the way. But we have an infinite number of points remaining in our interval, yet we've removed the entire interval. That is the Cantor set. Very, very theoretically interesting set. If you do this slicing method forever and ever and ever, you're guaranteed to have removed a length of 1, the entire interval, yet you have an infinite number of points remaining. I just find that to be fascinating to me. And so prove that as we do this process forever, we have removed an interval of length 1. However, note there's still an infinite number of values remaining within the sparse set. Pretty darn cool, I think. Anyhow, that ends section 11.2. That style of question, I can't say it's not going to occur on the homework. There is a question somewhat like that on the homework. Not exactly, but somewhat like that. So it's the very end of the homework. Or actually, I think I randomized the order of the homework because there were too many questions that were kind of neighboring in ideas that I wanted to be random. So there's one that has a picture and a figure, a triangle with things moving around. That's this style of problem, sort of. So watch out for that one. Anyhow, we are done for the day. Just to let you know, we are meeting on Friday. It's the last day prior to spring break. There will not be a quiz on Friday, even though technically we should have one. There won't be one because I'm leaving town and I don't want to sit in my car and watch you guys and stuff like that. So can I scroll to the bottom of the page? Yeah. Do you want to see the full page at once or just the bottom of the page? Perfect. There you go. This is what made me fall in love with mathematics. This type of idea where it's just kind of, you have to really think about it and ponder it. This stuff has just always been beautiful to me. So this, along with, I think we did one a while ago, which was the area underneath 1/x is infinite, yet if you rotate it around, it's a finite volume. I just find that to be just beautiful stuff. Anyhow, you guys have a wonderful Wednesday. I will be here for office hours in about 11 minutes. Otherwise, Be safe, have fun with whatever you're doing today. Do some studying. Remember, 11-1 is due tonight. 11-2 is due the Monday after break. I think that's right. Yes, that is right. So get started on it earlier than later, because you want to be able to, have time to think about it. All right. I'll be back in about 10 minutes. Take care, everybody.